So many thanks to organizers that I have the opportunity to talk about some work in progress with Hans and Matthias. And this is about quilts. So, okay, there is a slight problem now because it's not reacting in any way. I got one. Okay. So, I guess this is about ASMs, and one guise of ASMs, this guise maybe, are the corner sum matrices, which we have seen just before in Anna's talk. And actually, I think these are the objects I like most. So an S times T corner sum matrix is a map. We should think of it as a matrix from the set actually 0 up to S and 0 up to T to the natural numbers with the natural conditions. So in the first column, we want to have zeros. In the first row, we want to have zeros. At the very end, we want to have the maximal possible entry, and this entry is maximal possible because in every step we are allowed to increase only by 1 at most. Okay, these are just the corner sum matrices. And one nice thing about these corner sum matrices is they form a lattice. Yes. And there is another nice thing about these corner sum matrices. We'll see in a moment. Oh, that's very interesting. Okay, I forgot. So here's a picture we just saw, I think. I should have taken a photo and slapped it in, but yeah, the setup is very brittle. Since this is 42, so don't be, okay, you never go back. This is for 42, and you see nothing. It's too big. Yeah. I said there is another nice thing about corner sum matrices. The corner sum matrices, I would like to go back now, but I can't, where matrices, S times T or something. And instead of matrices, we could look also at the product of posets. And a matrix is just a function from the product of two chains to the natural numbers, a matrix with non-negative integer entries, two chains to n. And now we can replace the two chains by anything, no? And the conditions just work. So we want that, so to say, the first column is all zeros. And the first column now means the elements correspond where one of the elements is 0, is the bottom element. And same for rows, so to say. And again, in the at the other end of the product, we want to have the maximal possible element. And yes, I write min here, but the maximal possible element it is because we increase by at most 1 whenever we cover. And nice thing about these form a distributive lattice, which is, I think, quite obvious. And yes, I don't have a picture for a quilt actually, because they are huge. So if you take any poset Q, S, and another poset T, and they don't have very few entries, I mean, yeah, you will have the chain essentially for getting a small quilt. So I don't have a picture for quilts. But if we have a distributive lattice, we can make the information smaller. We can reduce to the essential bits of information. To prepare to this, I show you a picture of some bounded graded posets. So what does bounded mean? We have a 0 and a 1. And what does graded mean? The 0 has grade 0, and as we go up, we increase by 1, and all chains have the same length. Okay, so the notation is just that I write the rank of the poset as a subscript. But it's not so important. These are the four posets we will see in the talk. So the chain, the Boolean lattice, A is for anti-chain, so it's an anti-chain with bounds. So anti-chain together with a 0 and a 1 element. And Z2 is interesting. It's the zigzag poset together with a 0 and a 1, or also known as the fence. And this will come up very soon. Okay. And yes, why bother? So that's actually the main question of this talk. Why bother? So I already said that if I take two chains, we get the corner sum matrices, because that was the generalization we started off with. And this was actually the invention of quilts by Sarah Bille and Matthias. So we get rectangular alternating sign matrices. And now let's look for other quilts which are interesting. And one example we found, it's new, are if we take the quilt built by this zigzag poset with another zigzag poset. And in this case, we get K times L binary matrices without adjacent ones. Yeah, okay. Which is somewhat nice, I think. And there's another reason why bother. We get some, very little, but some enumerative formulas. For example, if one of the two posets is a chain, and the other one is this anti-chain with bottom and top, we get a nice sum for the number of elements, for the number of quilts. In fact, something very weird happens. If one of the posets is a chain, we actually get a polynomial in S whenever S is larger than the rank of the other poset, which is nice. If one of the poset is the chain of rank 1, so just 2 elements, then the size of the quilt's lattice is actually the number of antichains in T, which means that we cannot hope to be able to compute the number of quilts in general, because we cannot even do it for the Boolean lattice on 10 elements, I think. So 9 elements we can do recently, but 10 elements is currently not possible. We do not know the number of antichains of the Boolean lattice with 10 elements. Okay. Yes. That's right. Yes. I announced that this 42 elements distributed lattice was too big. And I said I would like to reduce to the necessary information. And what's the necessary information? So if we have a distributive lattice, then we can call Birkhoff, and he will tell us that we need one definition. An element of a lattice is join irreducible. That's the irreducible from the title. If it covers precisely one other element. Birkhoff will say this in a different way, but that's the way I think of it, because it's very geometric. And then the theorem is any distributive lattice is isomorphic to the lattice of order ideals of its poset of join irreducibles, and that's also called the fundamental theorem of distributive lattices, and this is very nice. And yes, we can also remark that the lattice is distributive if and only if it is graded, and also its rank, number of join irreducibles, and number of meet irreducibles coincide. So we will have nice lattices in the thing. And so what we do is we reduce the information we have. So here is the poset, actually the lattice, sorry. Anna showed us. And if I just take the join irreducibles, I get the thing on the right-hand side. So maybe you can see in green, I highlighted the elements of the corner sum matrix which you can decrease. This is also the answer to a question I think we had before. And if there's just one green element, then it's a join irreducible. Then there's only one way to go below. Yeah? So the join irreducibles are just those rank matrices, corner sum matrices, where there's exactly one entry I can decrease. Okay. And this is the same thing for the 42 element lattice, and you will agree, this is much less information to remember. Okay. So now there's one theorem in this talk, which is this. Something interesting happens if I take, and I actually don't know whether this was known for alternating sign matrices. If I take the join irreducibles of any quilt lattice, so of any lattice of quilts, then I will actually get a graded poset, which is somewhat strange. So we know that distributive lattice is graded, of course, but in this case, also the poset of join irreducibles is graded. And I don't know, I would like to know whether this has any consequences, but it is nice. Yeah? And we can describe this poset in a very easy way. It's essentially all triples. The first element is in the first poset, the second element is in the second poset, and the third element is some number with bounds. And the covering variation is not so nice, but it's okay. And we can even compute the rank function, which is also very easy to compute. So yeah, this is the main theorem. Maybe this is a good place to ask for questions. So the M is a typo and should be R. Thank you. No, this is not a typo. M is the maximal of the rank. Sorry, M is the max at the very top. I don't have a pointer, unfortunately. Here you see M is the maximum of the two ranks. And so I put all the numbers you have to compute from P, Q, and R at the beginning, and then you just add the correct constant to make it a rank function. So we always start with 0 and go up. Yes. Yeah. 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 For rectangular alternating sign matrices. Okay. Yeah. Okay. Yeah. Okay. Yes. Also, moreover, this is not very surprising. We actually can give the bijection between this poset of irreducibles to the join irreducibles in the big lattice. This is not very difficult. So the bijection, it always involves max and mins and whatever. And here it also involves an interesting function, an interesting distance in a graded poset, which only works for graded posets. So it's the up distance. You have two elements, X and Y, and then there will be a shortest path from X to Y in the Hasse diagram. And within this shortest path, you just count the number of up steps. And this is well defined in a bounded graded poset. Okay. Yes. And here is how such a poset of irreducibles looks like. So this is a product of the two chains times this interval in the natural numbers. And you can see it's not completely evident which elements appear as minima, which elements appear as maxima, and so on. And also the covering relation is maybe if you just see this picture, it's maybe not so obvious, but still you can do it and one can work with it. So what can we do with it? One thing that's makes this what we can compute using this tool are the rank generating functions of the poset of irreducibles. So we cannot, this does not work for the big poset, for the interesting lattice. It just works for the poset of irreducibles. So for example, it's easy to see that the rank generating function of this poset of irreducibles is symmetric if both of the individual rank functions are symmetric. And the most interesting case is actually when I put in two identical posets. And in this case, this is an if and only if. And for example, for the alternating sign case, alternating sign matrix case, we can compute some rank generating functions. I guess these were known, but I don't know. So they are particularly nice if we have square matrices, but also if one size is much larger than the other one, we get a nice expression. Yeah. In this case, it turns out that the rank generating function is unimodal. That means we have few elements in the lowest rank, and we grow up to the middle actually, and then we have fewer elements in each step again, and we can compute the number of elements with largest rank. This gives us some kind of dimension. Yeah, we can do some things. And finally we can, oops. Now I have to go this way. We can also do some things for the Boolean lattice case. So as I said already, the number of quilts, the size of the distributive lattice for BS and BT as the two posets is completely hopeless to compute. But we can at least compute the number of joint irreducibles, and that's I find this actually quite BS is Boolean, yes. So Boolean of rank S and Boolean of rank T, and if S is less or equal to T, using this description of the poset of joint irreducibles, we get this interesting enumeration. Yeah. And actually, this is all I have to say. So my main question is, why should we look at quilts? Why should we look at the poset of joint irreducibles? And most importantly, which I would really be interested in, if the poset of irreducibles is graded, what can we say about the distributed lattice? Because this is a situation that happens frequently, and it seems that so all the people I asked said yes, that's the natural case, but these are special lattices then. So yeah, thank you for your attention.